Okay, thank you. Yeah, so I hope you are able to see my screen now.
Yes, sir.
Okay, cool. So today we'll be talking about, so we talked about paging last time, and today we'll be looking at this thing called swapping and what are the mechanisms for it. And there are some policies also related to it. So today we'll be talking about that. So why do we need this? So the question is that what if the memory space is doesn't fit all the pages? Or sorry, the memory space does not fit into physical memory. Okay. So in that case, we need to use some larger space and probably slower. And that's where the hardest drive comes in. And this is like, yeah, needed to support large virtual spaces for a large number of processes. Because there can be many processes running at the same time, and they might have like huge address spaces which might not at the same time fit into the memory. So for that, we want to utilize the space on the hard disk. So the first idea is the swap space on the hard disk. So this is reserved space on the disk. So I'll be using just disk sometimes for hard disk drive. For swapping pages in and out. Okay. So who will be doing this? The OS can read, write pages onto the disk into the swap space. And for that, OS would need to know the addresses. Okay. So let's just see an example that why this might be needed. So suppose you have a very small physical memory of just 4 frames. So it can hold just 4 pages. And suppose your swap space is 8 pages. So suppose this was physical frame number 0 to physical frame number 3, and this is block 0 to block 7 in the, so this is physical space, the physical memory, and this is the disk. Okay, and suppose how at some point things might look like that. Okay, here is process 0 with, and the page 0 of this process is residing at the physical frame number 0. Here is process 1, VPN 2, process 1, VPN 3, process 2, VPN 0. So at some point of time, maybe the physical memory looks like this, and maybe the disk swap space looks like process 0, VPN 1. So VPN 1 is not in the physical memory. Process 0, VPN 2. Suppose this one is free. Then you have process 1, VPN 0. Process 1, VPN 1. And suppose here you have another process like process 3, VPN 0, process 3 or process 2, VPN 1, and then again process 3, VPN 1. Okay. So suppose the swap space looks like this. So you see that here some processes which are completely inside the swap space. So what does that mean? That means that these processes, or in particular this process currently, process 3 is not currently running. Of course. So from this example, you can see that even though the physical space can be very small, the swap space can be used to like support a larger virtual memory, which cannot fit into the physical memory at one point. Okay. And just like one point to note that swap space is not the only place from which page in out happens. So what I mean by that is that suppose what happened was, so specifically for code can be brought directly from disk. So in case of code, what can happen is that suppose you brought in the code, the page belonging to the code, and then now you don't need it, like you need to free up memory, so you just remove it. And when next time you need it, you don't go to the swap space, you go to the original location from the from which you got the um, code the first time, and then you bring back the page which has the code again. Okay. So just this was a point to note that it's not that only the swap space which will be used for these things. Okay, is there a message or something? Okay, you can see. All right. So Yeah. Now to support this, there is some hardware support needed, and it is in form of present bit. If you remember when we were talking about page table entries, then we talked about it. So suppose we have a hardware managed TLB. Okay. And on a TLB miss, the hardware goes to the page table entry, right? And then look at the VPN index. Okay. And then go to the physical. So then you can see that the physical address translation might not be present. So there is a possibility, right? That so what did we say just now? That maybe all the pages are not there in the physical memory. So how will it be found out? So you go to the page table entry, and then there is the like there is the entry for the page, and there how will this be told that this particular page is not in the physical memory? This will be signified by present bit to be 0. Okay. So if present bit is 1, do as before, like go to the physical address, execute instruction, copy the thing into TLB, and execute the instruction. And if present bit is 0, then raise an exception, page fault, and ask the OS to handle it. So what is a page fault? Page fault is when a page is not present, the page being accessed is not present in the memory. That is called page fault. And the OS handles it via like suitably named thing called page fault handler. Okay. So now, what does the page fault handler do? So first thing is, how does the OS know where the physical page, where the page is, right? Okay. So generally, what is done is that in the page table itself, in the page table entry, okay, use the PFN space, the physical frame number space, to store the disk address where the page resides. Okay. So what happens on a page fault? OS uses IO request to fetch page from the disk. Okay. And when IO completes, the OS will update the page table entry. So basically add the address, mark the present bit to be 1. Okay. And then after this, it will result. Why this had happened? Because there was a TLB miss. So this may result in a TLB miss again. So then retry the instruction. So might go to TLB miss. Then go to page table entry, insert into TLB, and then again retry. And this time you'll get a TLB hit, and then you process as usual. Okay. So this is the control flow. I'll write the OS part a little bit more in detail. Okay. So yeah, there's another point that while IO is happening, the process goes into block state. So other process can run. Because IO will take time and it is not very wise to waste so much time while the IO is happening for this process itself. So you can run other processes, right? So this is what happens. But there is another point that what if the memory is full? So where does the OS fetch? So what if the memory is already full? That is the question, right? So maybe there is no space in physical memory to fetch the page from disk. Okay. So what does that mean? That we need to remove something. To what is called page in a page. Okay. So bringing back a page from disk to physical memory is called paging in. And for that, we need what is called a page replacement policy. For page out. To find which page goes out, right? And these policies are really important because these things can make a lot of difference. So in speeds, so we'll see an example. So for now, just remember that decision is important as it can make a huge difference in performance. Okay. So we'll see for the rest of the lecture, we'll be looking at like after describing the OS control flow in a little bit more detail, we'll be looking at the policies in the rest of the lecture. Okay. But let's just look at the control flow. So suppose the TLB is hardware managed. So for hardware, it's going to be exactly the same. Except check for present bit in page table entry after going to the page table entry in case of and even in case of a TLB hit, but generally if the page is in the TLB, then it is also so this can be a convention that can be there that if the page is in TLB, then it will be in the physical memory. But even in the TLB, there is a present bit which can be checked to know whether this is present or not. And in that case, but I mean that is not what is usually done, because then you are storing the disk thing here and so on, and this page is actually not there in the memory. So the reason why this page is not there in the memory, because it is not being used, and if it is not being used, then populating the TLB with such an address is not very efficient. So same, except check for present bit in the page table entry in case of TLB miss, and then raise an exception. Raise exception page fault if present bit is 0. Okay. Now what does the software do? So software need to do something in case of now the exception has been raised, so software needs to do something. So the page fault handler does the following. So suppose first it will find the physical frame number, which is where the page is going to be brought. So find free physical page. Second, it's going to be if no free physical frame is there, then you need to do something to replace. So evict page. So this is going to be the page replacement algo. Then you do discrete pt dot disk address into the PFN. Okay. And then you set the present bit to be true. You put the physical frame number there. And finally, you retry the instruction. So this is the control flow for the OS, and this is for when there is no free space. This is the page replacement algo. And this is the discrete, right? And process goes into blocked state. Okay. And so this is the control flow, but there are a few like caveats which or improvements upon this. That one is that OS might not wait till memory is full to evict pages. Okay. So for that, there are two variables called low watermark, which the OS maintains, and high watermark. So whenever number of free frames is less than low watermark, then OS runs a thread to evict pages such that number of free frames is at least high watermark. Okay. And so this thread is for freeing up frames and is called swap daemon or page daemon. So this runs in the background. And so now, whenever this happens, this runs in the background, evicts the pages to make up space so that next time, whenever OS needs, there are some free pages there. Okay. And what this tries to take advantage of is that evicts many pages at once. So results in one large write on the disk. Rather than many small ones. And this is like more efficient, as we'll see when we go to like file systems and disk drives and so on. So this is uses this idea called clustering or grouping. So that is the name. So this was just an aside that, okay, this might not be that, OS always, waits for the physical memory to be full and then only does the replacement. The replacements can happen like before. Okay, good. So now let's come to policies. So the policies are going to be about how to decide which page to evict. So that is going to be the question for the rest of the lecture, or that is going to be a very central question. So before we get into this different policies and so on, let's see why this is so important. Okay, so main memory it holds a subset, right, of all the pages. So it works like a cache, right? And what do we want to do? We want to minimize the cache misses and maximize cache hits, right? So this is what we are going to do. So how do we measure the performance? So the performance measure is going to be it's called average memory access time. Okay. And what is the formula for it? It's like quite intuitive. It's very simple. It's Tm plus Vmiss times Td, where Tm is the cost, that is time taken to access physical memory. Td is disk. And what is this Pmiss? Is probability of not finding the data, finding data in cache. Okay. Okay, so sometimes what is also done that this Pmiss is also measured. So here we talked about probability, but it is also measured in percentage. Okay, miss rate. Okay, so what is so like just to take an example, like again, so 10% miss rate would result in P miss to be 0.1, right? Because it's 10 over 100, so it's 0.1. So as you see, like there is always a cost of accessing data, right? But I mean, so the machine, sorry, the physical memory access will itself, cause you some time, and then that will be the cost of the accessing the data in case of the machine access. But if there is a miss, then we need to pay more for disk access, right? So, so just like miss rate, there is also hit rate. Hit rate is 100 minus miss rate, and P hit, the probability of hitting, is equal to 1 minus P miss. This is like quite obvious and intuitive. Okay. Okay. Now let's see an example to how these things actually affect your whole performance and so on. So suppose the disk access time was 100 or 10 millisecond, and the memory was 100 nanosecond. So memory is much faster than the disk, of course. And let's say that hit rate is 90%. So first hit rate is 90%, right? So what is going to be the average memory access time? It's going to be 100 nanosecond, which is the TM plus 0.1 times 10 milliseconds. Okay. And this will turn out to be, so 0.1 times 10 milliseconds is going to be 1 millisecond. So plus 100 nanoseconds. So it's going to be 1.0001 millisecond. So this is approximately 1 millisecond. Okay. So if the hit rate is 90%, then the average average cost for accessing the memory is approximately 1 millisecond. Okay. Now suppose the hit rate was 99.9%. Then what do you get? Then you get 100 nanosecond plus 0.001 times 10 millisecond. And this is going to come out to 10.1 microseconds. So approximately 10 microseconds. Okay, so you see that, this is 100 times more. So this was 1 millisecond, and so 1 millisecond is 10 to the power minus 3, and 10 microsecond is 10 to the power minus 5. So this is 100 times improvement. Okay. So like the hit rate, so just imagine that one memory access is 100 times more faster than in some other case. So the machine is going to run 100 times faster effectively. So that is why even small changes in these rates hit very hard. And if the hit rate approaches 100%, then the average memory access time will approach whatever is the machine time, 100 nanoseconds, which is very small. So this happens because the cost of disk access is very high. Right? So small miss rate, if there is a small miss rate, would still dominate or in case of a small miss rate, the TD would still dominate the AMAT, right? So for this reason, we need very good policies that minimize miss rate. Because as I said, even small change in the miss rate or hit rate would can result in drastic performance improvements. So a lot of studies have been done on this, that how do you measure the performances of different policies under different workloads and so on. Okay, so let's now start with the policies. That what are the policies? This was just to emphasize that policies are really important. Okay, so the first one we are going to look at is the optimal replacement policy. But since we are going to study policies and not just one policy, so that should tell you that, of course, this is not this cannot be implemented. So this was proposed by already. And way back in 1966, and this is like very simple and intuitive policy, so you can prove this to be actually the optimal. So what does it say? That replace the page that is going to be accessed furthest in the future. Okay, so this is what the policy says, that okay, look at the current pages, look at the future, and see which page is going to be accessed the last among these, and you replace that page, right? So this will result in fewest possible cache misses. And why? What does it say? It just says that basically other pages are more important, right? Why? Because they will be used before, simply because of that. So they'll be accessed before the page to be thrown out. Okay, good. So of course, as I said, this policy is not possible to implement, or if you find a way to implement it, yeah, that would be great. You can write a paper and be famous. And this basically works as a comparison point for analysis. Okay, compare with the other policies. So there are some examples like in the book that I would request you to go through with. And yeah, so I'm not going to do the examples because like you can just work them out if you know the policies. So that will not give any more insights or anything. But I'll discuss the key things that come out of that example, right? So just before that, there are just an aside that there are two kinds of cache misses. So one is called cold misses. So what is a cold miss? A cold miss is when the page is brought in for the first time. And it does not matter which policy or what you use, this will always going to be a page fault. This will be always a page fault. So the first time a page is brought in, then it is called a cold miss, which is going to be common. And then other is called capacity miss. So there's another one which we'll not be looking at because that is not going to happen in this case. So this happens because the cache was full and the page was paged out. Okay. And we can calculate the hit rate, miss rate in both cases, just remove the cold ones and, then look at the data and so on. So generally what people do is remove the cold ones and then look at the rest of the, compare the rest of the performance. Okay, so this was the optimal policy. And Now, of course, as I said, this is not implementable. So what is the easiest implementable policy? Any guesses? It's called first in, first out, or FIFO. So, of course, as the name suggests, this is like pages are placed in a queue. Okay. And when they enter the system, and when we have to evict, we evict the first one to come in the queue. Okay, so I mean, I just wrote in words, but I guess you all know what is first in, first out. Okay, so what is the advantage of this one? It is quite simple to implement, right? But what is the problem with this? The problem with this is that it does not care about which which page is important, and while pushing it out and so on. So okay, so that's why this will lead to like bad performance in many cases. Okay, and there is one very intriguing thing, that the performance of FIFO can go down even even when we increase the size of cache. Okay, so this is called Bilardi's anomaly, and you like if this sounds strange to you, as like it did to me, and you can see the example in the book that why this can happen, and this can happen because of you know FIFO does not have what is called stack property. So what is the stack property? The stack property basically says that whatever is the pages in like some size k cache, then if you increase the size of cache to be k plus 1, all those pages will still be present. So if that is the case, that if something has this property that all those pages are still going to be present in the k plus 1 sized cache, then of course there are not going to be more page faults in that case. So this anomaly can happen for like strategies or policies which do not have this property, for example, FIFO. So this is the first like simple policy that we had address, and second is going to be random. So as the name suggests, just replace a random page. Again, simple to implement. But like the performance or not might, it will depend on how lucky or unlucky you are. That whether the page replaced is going to be like, is going to be accessed soon. Okay. So this is like, a very simple this thing. But now there are some like history based things like which try to optimize, which try to get into like, importance of the page. So one of them is least recently used, abbreviated as LRU. And again, like the name is like self-explanatory. But the idea here is to use the history to guess the future, right? So what is the problem with FIFO and random? So let's call it rand can replace some important pages, right? So this is what we want to avoid. But how do you know that which page is important? So, I mean, we can't see the future. So we look at history as guide. And the idea is that if a page has been accessed, maybe, or it's likely to be accessed again. And now, what does there are like these two ways to like look at the history. So one is frequency, how many times the page has been accessed, and the other one is recency, how recently the page has been accessed. Okay, and based on these two, we make the policies. I mean, there are two policies which can be made, and they rely on the is on the principle of locality that we have seen, like even in case of TLBs. And what does the principle of locality say? That the program has certain code sequences like loops and some data structures that are accessed frequently. Okay. So as I said, the two strategies are which come out of this is like least frequently used, LFU. So as the name suggests, replace the page that is used least frequently. And then least recently used. LRU, replace the page least recently used, right? So so these are the two variants of this history part that are there. There are some other variants also, like most frequently used, or most recently used, but they generally give bad performance for most cases. Maybe you can cook up cases where like they give good performance, but generally their performance is bad. And why this is so? Because they ignored locality. In fact, they go against locality. Okay. So what we have discussed like mainly four strategies. Let's say the first one was optimal, then FIFO, then random, and then least recently used. So let's stick to like least recently used and not like LFU. Okay. Okay, so let's so there are some examples in the book that, so I'll just go through their findings and not go through them in detail that what do they do. So there are some workload examples in the book that for different kind of workloads, how do these strategies perform? Okay, so first one that they see is like no locality. Okay. So there is no locality in the in the process. It just accesses pages at random. Then how do you think they will perform? So actually, what happens is that they all like RAND and LRU and FIFO, they all perform like equally badly or equally well, whatever you want to call it. Except of course optimal because it can see the future, right? So this is what happens, and this is not very surprising that when like you are giving some pages importance, but the program itself does not care about importance of pages or anything. So it is not going to give you any advantage. Second is called like an 80-20 workload. So what is an 80-20 workload? That there are 20% of the pages which are accessed like 80% of the time, and the remaining 80% are accessed 20% of the time, which is close to what actually happens. So in this, LRU actually performs better, and like you can guess why it does so, because it takes into account locality. So better than FIFO or random. Okay, but of course worse than opt. And finally, they look at something called a looping workload, where the program just loops through certain pages. Okay. So here something interesting happens, that if the number of, or if the capacity of the cache is smaller than the loop size, then FIFO and LRU will result in 100% miss rate, while RAND will perform better. Right? Why this is so? Because since it is looping through the memory, the whole thing is going to be like, now the first one is kicked out before the last one is brought into the memory. And since the first one is kicked out, now the next time it is going to be brought in, it will result in a page fault. Okay. But if not, then FIFO and LRU will have 100% hit rate, just like opt. Because now all the pages through which like it is going to loop again, here whatever misrates I'm writing is like after the cold ones. So let's not talk about the cold ones, and then let's talk about maybe. Okay, so this is like, these were some workload examples which are given in the book, and you can go through, like, you can look at the graphs, like, slightly in more detail, and that will give you, like, some insight into this. But let's come back to the implementation of these policies. Okay, so these are the policies, but how do you implement them? So suppose you want to do like, so let's see first the difference between like LRU and FIFO. So of course RAND is like easier, but it does not. Yeah. So let's see the difference between LRU and FIFO. So LRU, what do you need to do on each page access? The OS must update some data structure, right? To keep track and to bring the page to the front of the list. Because now this page is like, most recently used. Front or last, depends on how you implement it. But the main thing that I'm trying to say here is that the OS will have to update on every memory access this particular data structure. Okay. And in FIFO, you don't need to do that. The data structure or the list needs to be accessed only in the case of replacement. Otherwise, you just have a list, and if you are going through hits and not misses, then you don't touch the list. And if you're going through misses, then you like go to the list and evict the first page. Okay. So LRU, of course, demands then more accounting, right? So one way to do this is have some hardware support. Okay. So when the page is accessed, add a timestamp, and now you can this can be saved either in the page table entry, or the you can have can have a list of frames, and the entry will tell when it was accessed. So now on page fault, scan this list, find this recently used page, evict it. Okay. So that is the idea to implement LRU in one way, but again, this is going to be very inefficient. Sorry. So suppose you have 4 GB memory, 4 KB pages, typical scenario. So you have 1 million or 1 mega of pages. So even to to serve every page fault, you have to scan whole list of 1M entries. So this is of course not very practical. So then there is this idea of approximating least recently used. And this is what is called the clock algorithm. Okay. So this uses the hardware support in form of use bit. It's called or reference bit. Okay. So it just uses 1 bit per page in the system. And now this can be stored either in page table entry, or it can be stored in other list. But what is going to be the idea? The idea is going to be there will be something like, so you have a circular list of pages. You have this thing, and so the clock hand. So this is I mean, this is just a like schematic diagram. This is not how it's going to look like, but you have a circular list, and this is the clock hand. It's called. So the clock hand will point to some page at random. To start with, and So when a page is accessed, the hardware makes the use bit to be 0, sorry, to be 1. And from 0 to 1 is done only by the OS. And when does the OS do it? So
0 to 1, 1 to 0.
sorry, yeah, 1 to 0 is done only by the OS. And when this will happen, so suppose replacement is needed, then it will check the use bit of the page clock hand points to. Okay. And if this is 1, then the page has been recently used. Not a good candidate for eviction. So it will just set the use bit to 0. It's called clearing the use bit. And then check the next page in the circular list. Okay. And if the use bit is 0, then either it is not recently used or the OS went through all the pages in list and all of them were recently used. So then you can just evict this one. So basically replace this page. I mean, this is just explanation what the OS is going to, if the use bit is going to be 0, then the OS is basically going to replace this page. And if it is 1, then just make it to 0, move on to the next. And this is just one implementation which is like popular, but you can have any other implementation also which periodically clears the use bit. So basically and choose between 0 and 1. To decide which one to evict. So as you'll see in the book, this this gives performance very similar to least recently used, not like exactly the same, but like for a typical like 80-20 workload. Okay, good. There is another idea that is like used to enhance the performance. It's using the dirty bits or dirty pages. So earlier I had told that in the page table entry there is so consider whether a page has been modified. Why? Because if modified, then to replace it, have to write to disk because we need to save. Right? So this is expensive. So why not choose the page? So this is done by dirty bit. So like 0, that not modified, and 1 is modified. So it is dirty, right? So if modified, then like we have to save it to the disk, so which is more expensive. So why not choose one which is not dirty? So this can be put on top of this clock algorithm or any such like okay. So this is like generally the page replacement policies, but there are some the other policies also that the OS needs to like think about, like so two of them are like first is when to bring the page in memory. Ah. So there are two options of this, like one is called demand paging, which is when accessed. And other one is called prefetching. Guess which page is to be accessed. Bring it ahead of time. Yeah, like for it to be good, like performance wise, your guesses have to be reasonably good, and that can happen in case of codes, for example, that some part of the code is being executed, and then you want like the later part to also be executed, so you bring it. And the other policy is about how to write pages on disk. And again, there are two ways. One is one at a time, and other is in clusters. So basically, like collect many pages and write them together. And this is going to, of course, as I said, this is called clustering or grouping. And this gives better performance because, as I said earlier, one big disk access is or disk write is much less expensive than many small disk writes. And then there is other concept of like thrashing. that suppose the memory is completely full and every page access is resulting in page fault. So now the OS needs to deal with such cases because then basically the computer will run at disk speed, and there are two ways to deal with it. One is called working set. Run a subset of processes whose memory can fit in, or space to fit in the physical memory. And make some progress. So this uses this idea called admission control, which basically says like, do less, but make some progress rather than trying to do everything and not making any progress at all. And then other idea is out of memory killer. It just kills the using large memory. Okay. And there is a small problem with this, that maybe other processes were relying on this process, so they will not work either. Okay, so I mean, this is like, yeah, I was running out of time, but I hope this is like, the basic idea is clear. So in working set, you just make a subset of all the processes, and you run them whose memory can fit in the physical memory. And out of memory killer is just a very like Darwinian approach that okay, whoever is using more memory, you just go kill it. Okay. So this is what is there in terms of like swapping the mechanism and policies. So this finishes this module basically of virtual memory, and from the next time we'll start with concurrency. Okay. Any questions like quick questions about today's thing? No. Okay. Thank you. Let's meet on Monday. Okay. No questions. Okay.